Hello and welcome to this Electrical Principles training video. In this video we're going to continue considering our subject of resistors connected in series and parallel. In this video we're going to do some circuit analysis on a series circuit. Now that might sound very far removed from your everyday electrical installation work. However, this is a really important concept for us to be able to understand because it helps us to build up our understanding of the subject of volt drop and why that happens in a real life circuit. So make sure you stay tuned to the end of the video so you can follow the process of how we consider what's happening with the relationships between the resistance in the circuit and the currents and the voltages inside this circuit, and it's going to help you to answer some of those tricky exam questions that you might come across. So I've got my Loctronics board set up ready to go. I've got my Mega Avo 835 ready to go. We'll bring the camera in and we'll have a look at this subject. So as you can see, we've got a basic circuit set up on here with three resistors connected in series with each other. Now again, the purpose of this video is to try and analyse a series circuit to see how the voltages and the currents are behaving, and we'll show you the mathematical steps to do that as well. However, just some basic principles to start with. The first thing we've got to think about is how much voltage have we got connected into the system. So we're going to turn our multimeter, our Mega Avo 835, to measure voltage. And we'll measure what the voltage is. I need to have this on DC, so that's measuring DC now. And I'll just measure what the input voltage into the circuit is. So we've got here, we're coming out with exactly 12 volts, which is quite pleasing. So we've got 12 volts across our supply. So that's what we're putting into this circuit. Now, because these three resistors are the same, what we find is that there is a voltage across each one of these resistors. Now what we're going to do is measure the voltage across each one of these resistors and just try and figure out what those voltages are and how they relate to each other. So you can see there, if we measure across this first resistor, you can see we're coming out with a value of 3.968 volts, so just under 4 volts. And you can see here, if we measure across this one, again, we're coming out just under 4 volts, 3.978. And across this one, you can see there that we've got, again, just over 4 volts in this case. Now, what's interesting is if we take those three values together, we've got effectively 4 volts, 4 volts, and 4 volts. If we add those three values together, we get the supply voltage. So in a DC circuit, or in an AC circuit that is purely resistive, we can see that if the three loads are the same, the three resistors are the same, then we get the same volt drop across each one of these. And we're also starting to see that the voltage across each resistor, when we add those together, really we should say combine them, because that'll help us out with our AC theory when we get to that. When we combine those three values together, we end up with the supply voltage. So again, the typical exam question may show you a series circuit with three resistors connected to each other. If those three resistors have the same value, and the question asks you to find the volt drop across one of the resistors, you just take the total voltage and divide it by the number of resistors in the circuit. This, however, does start to get a little bit more complex when we start putting in resistors that have different values. So let's look at doing that next. Okay, so we've set up a different circuit now, which has an 18 ohm, a 10 ohm, and a 27 ohm resistor. Now, what we're going to do for the purposes of this experiment is we're going to measure the values of these resistors because they will be slightly different to the printed values, and we want this to be as accurate as we can to improve our understanding. So we're going to measure the resistance of each one of these and record it on a drawing and then show how these values relate to each other. So first of all, we're going to measure across our 18 ohm resistor, and you can see there that we've got 17.78 ohms. So we'll call that one R1, we'll put that on our drawing, 17.78 ohms. And then we'll measure across resistor number 2. And we've got there 9.89 ohms. So here you can see resistor number 2 is 9.89 ohms. And then we're going to go with resistor number 3, and you'll see there that we've got 26 26.51 we'll go with for that one. So R3 is 26.51 ohms. Now, in order to be able to analyse the voltages and currents that are going on in this circuit, we need to follow a number of steps at this point. And the first thing we need to do is find the total resistance of the circuit. Now, the way that we do that, so this is step one. Is we calculate total resistance. So we'll find the total resistance. Now, the way that we do that is we do RT, so that's the total resistance. Now notice the T is in the subscript, so we're finding the total resistance is equal to the value of R1 plus R2 plus R3. And when we add those together, so again, we've got these nice accurate values that we can use. So we've got 17.78 plus 9.89 plus 26.51. And we'll find when we add those values together, if we put that into our Casio FX83 GT plus, 17.78 plus 9.89 plus 26.51, we come out with an answer of 54.18. So we've got 54.18 ohms, and that is the total resistance of this circuit. The next step, step two, is to figure out what the circuit current is. So we're going to find the current. Now, in order to do that, we need a little bit more information, because to find the current, we're going to use Ohm's law, which we're nice and familiar with by this stage. I equals V over R, and that's going to be the total voltage divided by the total resistance. But in order to do that, we need to figure out what the total voltage is. So we'll measure that up now. So I'm going to connect my voltage into the system. I'm going to set this to measure volts. I'm going to measure the voltage across the supply here. So if I change that to DC and connect this up, so we'll power this up now, we should get our voltage measurement. So we've got there 12.1, yeah, settled at 12.18 there. So we'll go with 12.18. So the total voltage that we're applying to this system is 12.18 volts. So now we're going to find the total current, which is VT divided by RT. So we're going to say that we've got 12.18 divided by the total resistance of 54.18. So we've got 12.18 divided by 54.18, and that gives us an answer of 0.22. We'll round that to 3 decimal points, so that becomes 0.225. So we've got 0.225 amperes. So at this stage, it'd be a good idea just to verify that reading. So what we'll do is we'll set our multimeter to measure current. Obviously we'll disconnect it first because we don't want to go damaging the equipment. So we're going to change this now to measure current. And again, we're looking for DC current. So we'll set that to DC, and we're into a slightly different setting now. We'll go to milliamps actually. Although, no, we'll be getting more than 100 milliamps, so we'll leave it on amps. So we'll set that to amps, and then we will measure the current flowing into the circuit. Now, to achieve this, what we need to do is we actually need to disconnect a link out of the circuit, because the ammeter, now we've changed our multimeter into an ammeter, needs connecting in series. So what that means is we need to persuade the current to leave the circuit, go through the multimeter and back into the circuit again. And we do that by removing a link and then connecting up like so. So we'll set that to measure DC current. And you can see there we're getting 0.225 of an amps. Look how close, that's beautiful. Yeah, exactly what we're expecting that to be, 0.225. Okay, so now we know the current. That leads us on to the next very interesting stage of this. So let's restore the circuit back to where we were, because it is a really important principle to understand that inside a series circuit, the current is the same everywhere. So we've just measured the current here. It came out at 0.225 amps. If I was to measure the current flowing out of the circuit, you'd find that we'd get the same reading. So let's have a look here and see if that is the case. Let's see if we get the exact same reading again. So again, there we go. We've got the same current out as we've got going in. And actually what we'd find is that if we were to connect the ammeter up between the two resistors here, we'd find the same current. If we were to connect it here, we'd find the same current. In fact, if we could kind of crack open the resistor and somehow connect the ammeter in the middle of there, we'd find that we still get the same current. And that is a really important principle for us to understand. In a series circuit, the current is constant. The current is the same everywhere throughout the series circuit. Now that helps us to understand what's about to happen next, and that is a really important principle as well when we start talking about AC theory, which is much later in our area of study if you're watching these videos in order. So that brings us to our next step in this process. The next step is to figure out what the voltage is across each resistor. Now this is where this gets really interesting, because this starts to relate directly to our understanding of the circuits that we're installing out in the real world. So let's just have a look at what step 3 is going to be. So for step 3, we need to find the volt drop across each resistor. So what we're going to actually calculate here technically is the potential difference across each one of these resistors. So we're measuring the voltage across here. Now, in order to kind of get our heads around what's about to happen here, we just said that the same current is flowing through every bit of this circuit. So through this resistor is flowing 0.225 amperes. So there has to be a voltage across this resistor that is high enough to push 0.225 amps through that resistor. So how are we going to calculate, first of all, what that value will be? Well, we take Ohm's law, and we start Ohm's law by saying I equals V over R, and then we transpose it. So we want to get V by itself. So we would say, if we want to get V by itself, at the minute we've got V and we are dividing it by R, so we do the opposite action, which is to times by R. So we end up with V equals I times R. So we've done the opposite function there. Instead of dividing by R, we've times by R, which has moved it over to the other side, and we're multiplying that by I there. So let's have a look at this now. For resistor number 1, we will find volt drop number 1. So volt drop number 1 will be equal to I times by R1. Now the current flowing through the circuit, remember, is the same everywhere. So that's just going to be the same value for current that we calculated and measured, 0.225. And then we're going to times that by resistor value number 1. And we said earlier that resistor value number 1 was 17.78. So we're going to times that by 17.78, and we'll figure out what our answer will be from there. So we'll do that calculation, 0.225 times by 17.78, and we come out with 4.005 volts there. So we've got essentially, well, we'll write down the full answer, but that's basically 4 volts. Yeah. So we've got 4.005 volts. So now let's head back over to the board. We'll set up our multimeter to measure voltage, and we'll measure the voltage across this resistor. So we should be getting somewhere in the region of 4 volts. Set it to measure DC volts, because that's what we're working with. And you can see there that we've come out just a tiny little bit higher than we thought we'd be, but we are very much in the ballpark there. You can see 4.05 volts, so we're quite happy with that as a value. So we just repeat that process now to figure out what the volt drop across this resistor will be. So we've got there V2 will be equal to I times R2. Again, we've got that constant current, 0.225, times by the value of resistor number 2, which is 9.89 ohms, which we measured very accurately earlier on. So now if we do that calculation again, 0.225 times by 9.89, we come out with an answer of 2.2, let's go 0.225 volts. Okay, so we should get 2.225 volts. Let's measure that and see if that's accurate. Look at that, beautiful. 2.22, oh, look at that, that's just lovely. 2.226 volts. So again, we're within like 1,000th of a volt there. So that's a really nice result from that. Now, just think about that logically. What's happened here is we had a higher voltage across the higher value of resistor. So here we had our 18 ohm-ish resistor, and here we've got our 10 ohm resistor. So the same current has to flow through this resistor as flows through this resistor. But because this is offering a higher value of opposition to current flow, that means we need to give the current a bigger push across that resistor. And therefore the voltage has become higher across this resistor because it needs to be higher to push the current through there. So let's just complete this part of the process. We've got our final voltage now, V3, which will be equal to I times R3. Now, just thinking about this logically, we've got a higher value of resistor, about 27 ohms. So what do you think the voltage across here is going to be? Will it be higher than the 18 ohm one? Will it be higher than the 10 ohm one? Will it be lower than those? What does your intuition tell you? Well, let's do the calculation and figure it out. So we've got 0.225, there's our constant current flowing through the resistor, and then we're going to times that by, in this case, the third value, which is 26.51. So we've got 0.225 times 26.51, and that brings us to a lovely value of 5.965. We'll go with there, volts. Okay, so we've got 5.965 volts. So let's measure the voltage across this one and see what we get. And you can see there again, we're very, very close to the value that we were hoping for, 5.9. Again, it's kind of hunting about there, but we've got 5.9 volts, which is very close to what we said the voltage would be. And again, it makes sense that we've got the highest voltage here because this is the highest opposition to current flow. So we need to have the biggest push here to get that current to flow through the highest value of resistor. Now the final step is very simple, step 4, which is to calculate the total voltage. Now we know what the total voltage is because we've measured that already, and we've seen what that value is. But what we should find is that these three voltages added together should give us the total voltage for the circuit. So let's just do that now. We're going to say that Vt is equal to V1 plus V2 plus V3, which is equal to, in this case, 4.0005 plus 2.225. Now bearing in mind there's been a little bit of rounding going on here, 0.965, so the answer may come out just ever so slightly different. So let's see what that's going to be if we add this together. 4.0005 plus 2.225 plus 5.965, and when we add those together we come to 12.19, which is extremely close to the value we thought it'd be. Of course, there's been a little bit of rounding going on, which is why perhaps we're, I don't know, what's that, like 1/100th of a volt out, okay? But that's a very reasonable answer. We've come very, very close to the actual figure. So to help deepen our understanding for this subject, there will be a worksheet coming out on this with a accompanying video at some point, just to help us kind of reinforce our understanding of this and to be able to answer exam questions. However, we now just want to think very briefly about how this relates to our actual electrical installation work. There will be a future video demonstrating this principle a lot more clearly, but for now, let's just think about it like this. We connect up loads in a property. So let's say we connect a load up that has a certain resistance, and then we feed it with conductors. Now in this case, the conductors we've assumed to have no resistance. The resistance of these conductors feeding this load is so microscopically small that we end up with a very, very small volt drop across here. It's so small as to be negligible. However, in an installation, as these conductors feeding the load get longer and longer and longer, the resistance of those conductors gets higher and higher and higher. So what that means is that effectively these two resistors, we could replace these with the resistance of the conductors feeding that load. And that means that while these resistors would have very, very low value because the conductors they represent have very, very low value, nevertheless, there would be a volt drop across both of these. And so therefore, we can see that the voltage that we're applying at the start of the circuit and the voltage that we apply at the end of the circuit will be different. We'll have a lower voltage here. And that will depend on the length of the conductors, because that will change the resistance of these two resistors here that we could use to represent the resistance of the conductors, and also the amount of current flowing through the conductors. And when you calculate volt drop, those are some of the things that you have to take into account for that. So we'll do a more detailed video on the application of this a little bit later on. For this stage, we've done enough to show the steps for calculation, how to analyse a series circuit, and some basic application for this. So all that remains in this video is to say, thank you very much for watching.